Okay, so hi, welcome to this next video in linear programming. So this video is going to deal with the implication that all feasible linear programs have a basic feasible solution. And so this is the technical detail from phase one of the simplex algorithm. In phase one, if you remember what we were trying to do, there's two parts, right? In phase one and in phase two, there was some technical detail we had swept aside. And in phase one, what we were trying to do is generate a basic feasible solution to our linear program based off of just starting from scratch. And the way we did that, well, what we did is we constructed some auxiliary linear program, and then either that would correspond to the original linear program being either infeasible or it would have a feasible solution. And then we just kind of said that, well, the fact that it has a feasible solution just automatically implies that it has a basic feasible solution. We're just taking that for granted, and so now we're done. So this video is actually going to flesh out that fact that we've taken for granted there, about how exactly do you go from having a feasible solution to a basic feasible solution. So the goal is going to be then to provide an algorithm which starts us from a feasible solution to a basic feasible solution. So it's just kind of a technical thing, so we're going to provide the algorithm after a sequence of results. But just let me give you a rough overview of what's going to happen. The setting, well, let me not talk about the entire setting, but in a linear program, typically, in the standard formulation, there's some non-negativity constraints for these variables. And the idea is that if the feasible solution that you start at is not a basic feasible solution, then there's some sort of good direction you can travel in. So, all your solutions are points in space, high-dimensional space, and you just travel in some direction where you run into another solution, but the new solution is going to be it's going to be like an edge case. Basically, you're pushing in a direction so that one of these variable constraints. You see that non-negativity means either it's exactly equal to zero or strictly positive. So you're going to push in a direction that means that one of the components that was strictly positive is going to go down, down, down to exactly zero. And then once you hit exactly zero, you can't push in that direction any further. And so now you're kind of at an boundary edge case here. And the idea is that might be a basic feasible solution. And if it's not, then you can kind of repeat, and you can travel in another good direction where you maintain the fact that that variable that got pushed to zero stays at zero. So you're still in that edge case, but there's lots of, it's a high dimensional thing, right? So there's probably lots of different directions you can push in, and you push in different directions over and over again and keep running into boundaries until you're at the intersection of all these boundaries. And once you're at the intersection of enough boundaries, you're an even edgier edge case than you were initially. And then at some point, it's an edgy enough edge case that it's a basic feasible solution. So in some sense, that basic feasible solutions are the edgiest of all edge cases. You've pushed in every and run into every boundary that you could, and so that's kind of like a corner case in a sense. So there's a meaningful sense in which that's true, and that'll be fleshed out some later video. But anyways, that's just the intuition for now. So we're going to need to figure out how to travel in a good direction and so forth. So anyways, so let's just get on with the actual details then. So that's the idea. We're going to travel in good directions to run into boundaries, and then at enough boundaries you're to BFS. Okay, so BFS is basic feasible solution, of course. And so typical setting, we're calling this linear program P, as we've done before, and then we're assuming that A has linearly independent rows. That's the usual assumption. That's just, you can always assume that without loss of generality, and that just makes it easy because the column space is now definitely Rm, since the rank is exactly the number of rows, which is m. So it's an m by n matrix as usual. Everything's usual, and then we're just starting with a feasible solution, x bar. So x bar is a feasible solution for this program P. So in other words, a times x bar equals b, and x bar is non-negative. So this linear program P has x bar, feasible solution, and you look at the components of this feasible solution that are positive. So they're either going to be exactly zero, or they're going to be strictly positive. So look at the indices of this x bar that are strictly positive, and then those indices, you put them in a set called j. So that's what j is. It's a set of indices from 1 to n, and n is in 1 to n indexes the columns, and also the components of x, and so the strictly positive components get put in this index set called capital J. Okay, and the first fact is that about this set is that the columns, if the columns of the submatrix indexed by J, if those are linearly independent, then already X bar is a basic feasible solution. We don't know for what basis, but it's just for some basis, and that basis definitely contains all of the indices J. So we'll already be done in that case. So why is that true? Okay, so if the columns of this submatrix, if all those columns are linearly independent, then that means we have a bunch of vectors that are linearly independent. So extend that to a basis where you add in more columns of the matrix A to give you a basis of the overall space, and so that'll be B. So B is just an extension of J. In linear algebra, when you have a vector space, you can always extend from if you have linearly independent vectors, you can always extend to a basis. You can just that can always be done. So do that, and then for whatever basis you've extended to, X bar is a basic feasible solution for that basis. Yeah, so the conditions, we need A times X bar equals little b, and then also you can look at this picture over here. So J, it's the green circled set here. Those are the indices for where X bar is strictly positive. Extend that to some basis capital B, that's this. And then capital N is all the non-basic indices, that's just the rest. And so X bar N is going to be 0 because actually every component is strictly positive or exactly 0. And the only components for which X bar is strictly positive got put in J. So J lives inside B, and so actually even these other components outside of J but still in B, those are also zeros. But anyways, that's neither here nor there really. The important part is that all these components over here are also zeros. So everything outside J, all those components are zeros. So in particular, the non-basic components are. So X bar non-basic indexed components are zeros, and so that implies that this is a basic solution, and then you of course it satisfies non-negativity by assumption. So that's the third thing. I didn't write that down, but yeah, you need non-negativity, which we're assuming. So we have a basic feasible solution, and you get that just by extending the linearly independent columns of AJ to a basis B. So that's how that works. Okay, so so the idea is that if the columns of AJ are linearly independent, we're already done. We already have our basic feasible solution. On the other hand, in case 2, it could be that the columns of AJ are linearly dependent. And so in that case, that's when we're going to do this thing where we travel in a, quotes, good direction to get a new feasible solution, and then it's going to hit some boundary, and when you hit enough boundaries, it's going to, it gives you a greater chance to be a basic feasible solution. And you do this enough times, and then you'll be at a basic feasible solution. So yeah, here's a picture. So start at X bar. That's our initial feasible solution that we start with, and then you're going to travel in some direction D. D will be a good direction. By D we mean it's a vector in Rn, so that indicates a direction in this n-dimensional space, and possibly scale it. D is just indicating direction; it doesn't indicate how far. But so you just scale that all the way until you hit this wall here. And this wall represents, one of the constraints, non-negativity constraints. If you pushed any further in this direction, you'd cross over, and one of your components would be negative, and you don't want that. So X prime here is the wall, and so you push from X bar to X prime in this good direction, and you've hit an edge, and maybe this will be a basic feasible solution, but maybe not. And in that case, you're still at a feasible solution, so you push in another direction. But you do it in a way that you maintain the fact that you're already on this one edge, and you just push in this new direction, good direction, where you stay on this edge, and then you hit another edge. So now you're at the intersection of both these edges. And for instance, if we're in two-dimensional space, this corner point here, it's like, it's an even edgier case is what I meant before. Here's an edge, here's an edge. So it's a double edge here, or in other words, in two-dimensional space, that's a corner. And, and the idea is that's going to be a basic feasible solution, that corner point. So that's actually pretty meaningful in a geometric point of view. A basic feasible solutions really are corner points. That'll be made more precise in a later video. But yeah, so just push from boundary to boundary and maintain all the boundaries that you're already on until you hit a corner point, and that'll be your basic feasible solution. That's the idea. Okay, so yes, we want to travel from x bar in a good direction d in Rn to hit boundary cases and hence obtain a basic feasible solution. So how do we sensibly define this so-called good direction? So here's how you do it. So define d in Rn to be a good direction for x bar, the starting point. Here's x bar, the starting point. So d will be a good direction if the following three criteria hold. So you need at least one of those components indexed by j. You need dj to be negative for that component. So for at least one of them. And then you need d to be in the null space of the matrix A. So AD equals 0. And then third, you need that dj is a 0 for all components that are not in that set capital J. So in other words, d and not j is 0. Actually, this is a typo here. Sorry about that. I don't mean capital N. I mean lowercase bracketed n. Little n indicates all the column indices from 1 to little n. It's all the columns. It's, I mean this n, the n of the space that we're living in. Capital N is the non-basic indices. That's not what I mean. I mean just the complement of j. So all the indices, little n, except for j, because that's the complement of j. That's what I mean here. So those are all zeros. So actually, I might as well just do that now. I can just erase this if I'm careful enough, and let me just replace that with the correct little n, not j. Yeah, anyways, I know that's kind of messy now, but n, not j, is what we meant there. Anyway, so, okay, but the real condition was right here. So dj is 0 for all j that aren't in this capital set of indices j. Okay, and so that's what a good direction for x bar will be. So now we want to start exploiting this definition to show that this helps. So so if the columns were linearly independent, we already showed that we were at a basic feasible solution for some basis. If the columns are linearly dependent for these j indices, then the implication is that there is a good direction d for x bar. So there is a good direction that we can travel in. So it was, the way I drew that picture, it wasn't really clear how you knew that there was going to be a good direction, but there is. So that's what this fact is saying. So here's the proof. So if the columns of AJ are linearly dependent, then that means I can take a linear combination of the columns of A indexed by capital J here. So A little j times D little j, that linear combination. So D's are scalars, of course, and that's going to give us 0 because that's the definition of linear dependence for some DJs that aren't all zeros. And so those correspond for the indices capital J. And so now what we're going to do is we're going to extend that to an overall vector D in Rn, where the complement of J, so D sub n not J, those are all zeros. In other words, you already know what the J indexed components of D are. That comes from whatever the linear dependence of the columns here was, and then you just pad with zeros for all the other components. Okay, so this is supposed to work. So you can see that condition 3 is met. D n not j is equals 0. That's true automatically. We just padded with zeros for all those components. AD, we need that to be equal to 0, so A times D. So what is that? Well, it's, break it up into the j components and then the not j components. And for the j components, by linear dependence, AJ, DJ, That's this sum right here, which is 0. And then plus, for the other part, we don't know what the a is, but we do know that the d's are all zeros. And so, so this is just a times 0, which is, of course, 0. So you add everything up and you get 0. So D really is in the null space of the matrix A then. So that's good as well. So that takes care of the first two. The last one, there's two possibilities. So we already know by linear dependence that not all of the DJs are 0 for the particular little j's that are in that capital J index set. So and that's by linear dependence. The definition of linear dependence means that not all the DJs were zeros. So either one of the DJs is negative for one of those J's in capital J, and in that case you're good. Then you've met the definition because that's what we needed. That was the first criterion. Or it could be the case that all of the non-zero DJs were positive. That in other words, none of them were negative. And we know that if this blue comment, at least one exists. When I say at least one exists, I mean at least one non-zero component exists. I don't know that it's positive or not. I just know that at least one thing that's not 0 exists by linear dependence again. And so either it'll be positive or negative. If it's negative, we're good. And if all of them are positive, then you just negate this vector D. So if we're in this first case where it's negative, the first condition is now been satisfied, and if the second thing B happens, just replace D with minus D instead. That'll be the vector. So instead of traveling in the direction D, you just travel in the opposite direction. You go backwards. Yeah, and you can clearly it's still all those n not j components. Those are all still zeros because minus 0 0. A times minus d, it's just that's still in the null space. It's minus AD, which is minus 0, which is 0. And now one of the DJs is negative because it was positive before, negate, now it's negative. So in either case, there's a good direction. So it's either the original vector D that you choose based off of this linear dependence condition of the AJs, or it's the negation of that vector. Okay, and so now fact 3 is just kind of a synopsis. It's combining it, but it's the important fact that we need. So I kind of decorated it with this star here. So X bar, if it's not a basic feasible solution, then we have a good direction for X bar. So the proof is just combining these two facts that we've already established. So if X bar is not a basic feasible solution, then fact 1 tells us that those columns must be linearly dependent. Because if they're linearly, it's the contrapositive of fact 1, which is equivalent to fact 1. Because if they were linearly independent, then we could extend to a basis for which X bar is a basic feasible solution. But we're saying it's not a basic feasible solution. So they can't be linearly independent. They must be linearly dependent. And then this next fact that we just showed is that if those columns are linearly dependent, we must have a good direction, D for X bar. So yeah, so for non-basic feasible solutions, there's always a good direction, D. That's the important fact that we need. And then there's another important fact that we need, so I decorated it with a heart. So the star and the heart are the two important facts. So here's the second important fact. So fact 4 is saying that if X bar has a good direction, then there must be a. It's just saying what we already wanted. If we have a good direction that we can travel in, then there must be some feasible X prime for this linear program P, such that the indices for that vector J prime, we'll call them. It's the indices for where that vector is strictly positive. It's such that the number of such indices is strictly less than the number of indices from the original set of indices corresponding to X bar. So remember, J is the indices of the components of X bar that are strictly positive, and so J prime is the indices of X prime that are strictly positive. And we're saying that there's strictly less positive components, strictly positive components of X prime than there were of X bar. And so we want that as well. So it's important that this is strictly less. So for every time we travel in a good direction, we're going to have one less positive component. So and since everything is either strictly positive or exactly 0, that means we have at least one more 0 component. Okay, and so the proof for this is that if D is a good direction for x bar, which we're assuming from the start here, then here's the construction you do. You take x prime parameterized by a variable t, very reminiscent of a phase 2 simplex algorithm, to be x bar plus td. That's actually what we're going to define it to be. So x prime is parameterized by t, and like this. And so we know what d is. It's the good direction. So so you just fill in what t is, and that gives you x prime. But actually, it doesn't matter at first what t is. If you take yeah, so the comment here is saying that we want x prime of t to be feasible for some value of t. For any value of t, though, a times x prime of t, well, it's just fill it in. So it's a times x bar plus td, and you factor the a in, and then we part of being a good direction, d, means that d is in the null space of a, so this part just goes away. And so we're just left, so it becomes 0. So we're just left with a times x bar, and then we already know that that's b. So x prime of t satisfies the matrix constraints automatically because this vector d is in the null space. So good directions are in the null space of the matrix A, and that allows us, no matter what d is, to maintain the fact that this is the matrix constraints are satisfied. And the other thing we want is non-negativity to hold. So we want x prime of t to be greater than or equal to 0. Okay, and so we have to have that hold for both the indices that aren't in J and the indices that are in J, capital J. And so let's do the ones that in the complement of J first. So x bar for the indices that are in the complement of J, it's the corresponding indices, components of x bar plus td, and for x bar, we already know that every component that's not in J is exactly 0. J is the ones that are positive, so everything else is the ones that are zeros. So x bar and minus J is a 0 vector, and then similarly D is a 0 vector. That's, again, by a part of being a good direction. So we're assuming we have a good direction, and that's one of the conditions. So so we have x plus td for those components. It's 0 plus t times 0, which is 0, which is non-negative, of course. Again, independent of what t is. So we haven't actually had to restrict t to be anything in particular yet. But this last part will, because that was for the J complement of J components. Now let's look at the J components. So x prime of t for those components, it's the corresponding components of x bar plus td. And then we know that here, for the x bar of part, those are strictly positive by definition of what this index at J is. And then the final condition of being a good direction is that at least one of these components in the J index set of D is negative. And so actually you can't, so t you're imagining is some positive value. You're trying to, non-negative at least, you're scaling it up as much as you can. But the idea is that you can't scale forever because one of these components is negative, and that's going to keep decreasing this whole part here, and that's going to force us to hit a boundary. So t is the amount that we're scaling that good direction d by. So in the picture above, when I had a d pointing in a particular direction, I said we might have to scale it by some amount. Well, t is the amount that we're going to scale it by. So what should t be? One of the components of dj is negative. So define the k, capital K, to be the subset of those indices such that it is negative. So it's non-empty because we just said at least one of the components is negative. So k is the components where they are negative, and then so xj prime of t is non-negative if and only if it's true both for the components that are in J but not K, and for the components that are in K. Because we've already covered the things that aren't in J, so it's just the parts that are in K and the parts that aren't in K but are still in J. So for the parts that aren't in K, then it's the corresponding components here, and everything is non-negative automatically just by definition of everything. The x bars are in J, so these are strictly positive. I put greater than or equal to, but actually they're strictly positive. And then t is non-negative, and then d again, if the k's are the parts where it is negative, so the j not k is the part where d is not negative, so it's greater than or equal to 0. So everything's greater than or equal to 0. So no, again, no matter what t is, this part will stay true. But for the indices k, where dk is negative, that's the part we have to deal with. So x prime of k, the indices indexed of x prime of t indexed by k, those are non-negative if and only if the corresponding components are of x bar plus td for those components are non-negative. And okay, and so these are vectors, right? They're subvectors of the overall vectors x bar and d indexed by k. And so x bar, so you just move this to the other side. So x bar greater than or equal to minus t dk, and for one vector to be greater than or equal to another, that means each of the individual components. So this inequality has to hold for all the components in that index set. So again, entirely reminiscent of a simplex algorithm, how we chose t, and then that's if and only if. Now I'm just going to divide. I know that the dj's here are negative, so I'm going to divide over. So I'm dividing actually by negative dj. So for these particular components dj, we know dj is negative, so negative dj is positive, so I divide by a positive value, negative dj, and so that keeps the inequality facing the same direction. So t is on the smaller side, so t less than or equal to this ratio, xj over dj, for all the indices of j in k. So we need that to be true. So t can be no larger than any of these ratios. So again, it's just like simplex algorithm. You take t to be as large as you possibly can. T will be the minimum of those ratios for the indices j in that set k. And so that is the exact value that you want to take t to be. If you took it to be any larger, you'd violate being less than or equal to one of those ratios, and then that would violate, in turn, non-negativity of the original vector x prime. In other words, we're pushing past the wall if we take t to be any larger. But if you take t to be exactly this value, this minimum of these ratios, then you just bump into the wall. You're at the boundary. Okay, so just take a look and recap. What we were trying to show is that we were trying to show that the indices of this new x prime. So this is what we want x prime to be. It's for this particular t, you fill t in to be this, and that gives you x prime that we want. And the idea here is that there's more zero components, or there's strictly less strictly positive components of this. So what were the zero components of x bar? It was everything that wasn't in j. Well, that's still true for x prime. All those non-j components are still zeros, but also, in addition to that, there's at least one more zero component for x prime, and that occurs for one of these indices in k. That's by our choice of t. You took t to be exactly large enough that it bumped into a wall, basically. You can just fill this in. Fill in t. T is going to realize the minimum of these ratios, plug that back in to the formula for what x prime is. X prime is x bar plus td. For this value of t, you can see that you get at least one more zero component because of our choice of t, and then that gives us an extra zero component besides the ones that we already had. So we have at least one more zero component, and so strictly less strictly positive components then. So truly j prime, number of cardinality of that index set is strictly less than that of j. Okay, and so that's what we really need then. Did I renumber this? Fact 4. I think this. You'll have to check for me. I think this might have been fact 5 that we're on now. I misnumbered this possibly, but that's okay. It's just the next fact. And this is the final fact. I think this might be 5. Anyways, okay. So if our linear program P has a feasible solution, then it has a basic feasible solution. It has a feasible solution that is basic. So BFS. So we're just combining all the facts from above. So start with your, say x prime is our initial, so before we were saying x bar was our initial feasible solution, but let's just call it x prime now. So x prime is the feasible solution, the p that we're starting at, and if it's basic, then we have a basic feasible solution. On the other hand, it could not be basic. And then that the fact, I think that was fact 3 that we got decorated with a star. But anyways, whichever one got decorated with a star, we know that if our feasible solution is not basic, then it has a good direction. And then we know from the other fact that we decorated with a heart that because this vector has a good direction, that guarantees us that there's a new solution x double prime that's feasible, where x double prime has strictly less positive components than x prime did. And now you just kind of iterate this. So we're at a feasible solution, and we have strictly less positive components now. So either this new feasible solution is basic, in which case we're done, or you do the same thing again. Since it's not basic, it has a good direction, and since it has a good direction, then there must be some feasible solution that has strictly less positive components than it does, and so on forever. Well, not forever, actually. That's absolutely the wrong word to use. It's not forever. It must terminate. It cannot repeat forever because we have this fact that j prime is strictly less than j. So the number of positive components is strictly decreasing at every iteration of this. So you can't do it forever because you're going to run out of components to turn from positive to exactly 0. And that's corresponding to the fact that you're going to run out of edges to bump into. And yeah, so since you cannot continually strictly lower, at some point you're going to have no more positive components to lower. So it has to terminate at some point, and so at whatever point it does terminate, that's your basic feasible solution. Because if it wasn't, then you could iterate again. But we're saying at some point it has to terminate, so it must terminate with a basic feasible solution. So there you go. That's how you get a basic feasible solution. So so the algorithm that we would use implements the reasoning of fact 4. When I say fact 4, I really mean whatever this fact is. It might be 5, but this one. So if we have a feasible solution, then we have a basic feasible solution. This is the proof of it. Either it's basic or it's not, in which case it has a good direction. And if it has a good direction, then there's another feasible solution that has strictly less positive components, and to iterate over and over again until you finally get a basic feasible solution. So that would be the algorithm. And that justifies phase 1. So we said in phase 1 that if there was a feasible solution, then there's a basic feasible solution, and this is how you would achieve it. Okay, and so here's the picture. Again, this is the little tree. So you start with P, and then in phase 1, now we know for sure that either it's going to be infeasible or we'll get a feasible solution, which in turn means that we'll get a basic feasible solution. So that's what this is saying. So if it's infeasible, then either it's not. So if it's not infeasible, so if we don't travel down this branch, then we travel down this branch, and which we said was it had a feasible solution in phase 1, but now we're saying that feasible gives us basic feasible by the final fact. It might be fact 5, I'm not sure. And then so that's justification for the fact that there's just these 2 branches and there's no other branches. Either it's infeasible or it has a basic feasible solution. And then you combine this with the fact that in the phase 2 of the simplex algorithm, so this phase, you're either going to have an optimal solution or unbounded, and that is implied by the Bland's rule. And so that's the technical detail for phase 2 that we swept aside. So be on the lookout for that supplementary video as well to complete this tree and to guarantee us that this picture, this tree really is accurate for the simplex algorithm, and that the fundamental theorem of linear programming, which says that one of these 3 things must happen, really is true. So yeah, so be on the lookout for that. That's it for this video, so thanks for watching.